Hello everyone, and hope last session was useful to you. We'll be continuing more on the computer vision side. Sorry that I have to do the session from outside. It's just because of my sickness. I have to like for better fresh air. Today we'll mainly talk about how images are formed and how to do filtering, and then we'll get into the image transformations, and we'll do 2 tutorials today. So I know, again, it's a very quick intro just to get people acquainted with the history of computer vision. So we all know that at the end, what we're trying to, like a computer vision is like an umbrella of multiple methods that are trying to understand what is in an image. And usually this is like the sensing devices is just simple RGB camera, but it can be more advanced sensing devices beyond that. And we're trying to work on the algorithms that will interpret these images. So this could go from in scene understanding, like trying to identify the different pixels. So let me show you here. This is, for example, work that is doing something called the panoptic segmentation, where you're able to segment all the pixels in the scene, but also are able to separate the different instances for the something called the things classes, like the different car, different motorbike. So this is again trying that this is all under the umbrella of scene understanding. But so far you see here, nothing talks about how to understand also the depth and like going beyond explanation of what like identifying the objects and segmenting them. Let me show you here. So this is another work that again, it's just showing you some examples of works that are under the idea of like how to do scene and scene understanding. So you can, some of the works here will be able to create a form of a map, and we are able to retrieve the depth. So by depth, I mean like the distance with respect to the camera for the different points in the scene. So this falls under like 3D reconstruction. So all of these tasks are trying to understand what is happening in a scene. And in a video, it could even be beyond that. In video understanding, you're trying to understand the actions that are happening in a video. So all of these are under the umbrella of computer vision. And again, I'm just like showing you some of the potential tasks that you will get to learn more during the summer school. But why even do we care about the visual data? So there are a lot of statistics, whether on Facebook or YouTube. Like there is a lot of visual data we're acquiring, whether like if you're looking into Facebook, how many users which are posting their like photos, videos. If we're talking about like YouTube, how there is like 500 hours of videos uploaded every minute. So these huge amounts of data, it's beneficial for various reasons that you try to understand like whether the images or these videos and in different ways, whether like identifying objects or going to more on the 3D aspect. Now, for a very like a basic intro, it's also under good to understand how when it started, like there are from a neuroscience perspective. So some researchers were trying to understand the visual cortex and how as humans, this is where we are able to understand and interpret what we actually see and perceive through our eyes. So there is this two-stream hypothesis. So we have the ventral and the dorsal. So you can think of it loosely defined, like it's not exactly like that, but you can think that even how our brain works, we're trying to parse the what and the where. So the what, more like the color, shape, texture, identifying objects. Where is more on the motion, identifying any like moving objects or like depth. It's not exactly like that, and it's much more deeper like that than that, but this is again just loosely defined. And like some people find it interesting to learn how to encode, like do neural encoding, like encode what the brain is perceiving using what deep learning models we have in order to have a better understanding of these models. Another thing, another aspect that you need to consider when talking about the history of computer vision on how actually even like the basic sensing device like the camera started. So one of the pioneer scientists that started the earliest experimental and mathematical analysis of the phenomena like from the camera obscura is Hassan ibn al-Haytham, and he basically tried to describe how if we have a small, like what we call the pinhole model, and we will be, so this time we will be actually discussing the basics of the pinhole model. I'm actually wondering, just to make it a little bit interactive and to help me get to know you better. Hey, hello, Rachel, how are you doing? Anyone here wants to tell, like, are we already with the pinhole model? What is the pinhole camera model? You can participate whether on the chat or if you want to speak. Yeah, I mean, anyone knows about it? Okay. If not, that's okay. That's totally fine. That's the whole purpose of the sessions. I'm just trying to see, like, get to know you a bit more. But if we're talking about the pinhole model, we'll see that how they started with the like seeing how the images are formed within this dark room, where you have a small pinhole that allows the light rays to get emitted, and then whatever is outside gets to be recreated and formed in an upside version of it on the dark room wall. And this was what started like what we call as the pinhole model, and we will be even going beyond that when we have in our cameras a lens. But that's where it started. Also from beyond the sensing devices and beyond how our brain works and the visual cortex, the real start when people started talking about computer vision as a project to be able to understand what the camera perceives, it actually started from this MIT lab. I think it was in 1966 or something like that. And one of the professors was trying to start a simple summer project. Like in just one summer project, Marvin Minsky was asking one of his students to try to get a camera connected to a computer, get the images, and try to see what the like how to get the computer to understand what it saw through the camera. But then they realized, of course, that this is definitely not one summer project at all. It actually it eventually ended up being more than 50 years now of computer vision research, including multiple tasks from 3D reconstruction to recognition to segmentation to multiple tasks. But yeah, that's how like you would say the initial start of computer vision research. Okay, so I will here go through like the basic pinhole model and what does it actually mean. And even better, let me just use a laser pointer. So how the pinhole model works is we initially want to be able to understand how the how an image is formed. So we have a camera, but then we don't know exactly how the images and the pixels these we are perceiving. So in order to understand that, the first thing you need to understand is the pinhole model. So now we have here like our world, including a tree in 3D, and we have a certain point here. So this point is a 3D point, which means it has the X. Let me actually get better. Sorry. We have the X, Y, and Z coordinates of this 3D point here. And then we have our pinhole. And we want to explain the phenomena where when the light rays are emitted from this real world object and goes through the pinhole, we find this construction of an inverted image of this whatever is outside in the real world. So you will find here, let's look. So this is like a 2D profile out of it. So here we're only looking into the y. We are now ignoring the x. So consider only the y. And then we have the depth. So the depth will indicate how the distance from the real world object that we're trying to study, and our pinhole, which will at the end be the camera later on and the lens. And at the same time, we have here the distance between the pinhole and what we call image plane. This is also in our eyes, this is called the retinal plane. So this image plane here is where the images are formed. And so that's why it's called an image plane. In an eye, when we're like for us as well, this is how it works. So we also have a retinal plane that the images are formed upon before it goes through the processing in the visual cortex. So similarly, like the pinhole model applies for both. So this is here called the focal length. And then this is on the image plane, what will be formed. So you will see this point will get mapped, projected into a 2D point here. So this 2D point here has X and Y. So this is a 2D point on the image plane. Now forget the X. We're just going to focus now on the Y because now it's just a profile. So you will find this here is indicating the Y coordinate of this pixel, of this point projected location on the image plane. So this becomes like, what do you notice here? So we have identified the focal length, the Y, the depth, and this is the real Y 3D in 3D of this point. What do you notice about this triangle and this triangle? Anyone knows? Like, it's basic math.
That is reversed.
Yeah, no.
Yeah, so they are inverted. Yes. What else?
Like proportion, like.
Sorry?
Like it's the same triangle but smaller.
So there is some similarity happening, right? So this similarity we can represent through the ratio. Thank you. So we can have the Y over the 3D version of the Y. So this is the 2D one and this is the 3D. This ratio, so this part over this part, because of similar triangles, becomes equal to this side over this side. So this is the focal length over the depth. So then if I want to compute the projected Y, which is the projected 2D point that I'm, this is the one in question that I'm trying to study, you can simply use it, use as the focal length multiplied by the 3D point Y and the 3D point Z, the depth. So this can also hold for X. So X, the 2D point X, after projection, is going to be equal to the focal length multiplied by the 3D point X of the X of this 3D point over the depth. Does it make sense? Anyone has an issue? Okay. Yeah, I see. I think the pinhole camera is one of the earliest cameras. Yes. So yeah, thank you, Grace. Yes. So they started, as I mentioned, with the Hassan ibn Haytham. It was one of the early explanations of how images are formed. We'll see now how we will introduce the lens here instead of the pinhole. Okay, so now that we have seen how to do this projection, this is called perspective projection. What you see here. So an orthographic projection, which is you can put it as an assumption, but it's like, so if you perceive anything from any camera, it's dependent, of course, on the type of the camera, but mostly it is perspective projection, except that you can have some assumptions. So if you have a camera that is in a very high altitude, so let's say I have here a UAV, and this is the world model. This is my 3D world. Not a world model, sorry, this is a 3D world, and I have the UAV here from a very high altitude. It's almost very hard to perceive depth, and it's almost no perspective effect. So at this point, Y is just equal to the Y, X is equal to the X, and nothing like in how it will be projected into 2D. There will be just here like the building, the road, and so on. So you just take, like ignore the depth. Unlike here where we had this formula to help us compute the 2dy and the 2dx. But this one, you rarely use it. It's under a very like small scenarios and kind of a severe assumption. Okay, so if we are, now that we are studying the pinhole, so if you remember the equation, what do you think will happen to this y here, like the projected y, if this tree moved further away? So if I moved further away and the tree now is here, what will happen? So let's say now the point is here. What will happen to this y?
It will decrease.
So remember the equation, y equal f.
Yeah, it will decrease.
Yeah?
Not increase, no, decrease.
Sorry, what do you say?
I say it will decrease.
Decrease, exactly, yes. So you will see here, like if this depth got increased with this amount, what will happen to the y? It will decrease. So now this amount here is based on this ratio. So we know that if z increases, y will decrease. And we know that if f increases as well, so this will be the next example. So if f increases, what will happen to the y? Will increase as well, right? Like it's directly proportional. So it's inversely proportional with the depth, directly proportional with the focal length. So if I want to zoom in, like here, so this is here where I increased the focal length, so the projected y became larger. So this is, you can actually do that through like controlling the focal length can control how you zoom in or zoom out from your image. So this is here on a very high focal length. So you can see the house very well. On a very small, this is the same object. So this is again talks about like the pinhole model. Now that we understand just the basic, like how to project on a 2D plane, it's important also to understand that we have a camera coordinate system. So for now, we only have a pinhole. We will discuss a bit later how to introduce the lens. But let's assume for the pinhole, the camera coordinate system will have the I and the J and the K. So this is the 3D coordinate system where the K is going to be aligned with this optical, something called optical axis. So this is perpendicular on the image plane. So this is here again, this is the image plane. And this is perpendicular on this image plane, this optical axis. And not to forget that the focal length represents the distance between our pinhole and the image plane. Now, let's introduce the fact that we have multiple light rays. It's not just one light ray. So I can have here a full object, whatever that object is. If you increase the pinhole into a large pinhole, it will allow more light rays to go into it, which will make like it will create problem because it becomes blurry. So with blurry image, so this is here the aperture size. Like you have some pinhole here with like you can think of it as an aperture, and we'll talk about the we'll see the camera how it's constructed in a minute. But if you have a very large aperture, you ended up having blurry images because it's just entering so many rays. So when it's constructing this to a 2D projected image, it will lead to this blurriness. Now, if you have a very small aperture, it will lead to dark image. It's gonna be sharp. So this is sharp, but it's dark. So that's why they introduced the idea of the lens. So instead of having just a simple pinhole and you're controlling like whether it's a small or a large pinhole, you actually can use the lens in order to make sure that even if you allow multiple light rays, like more light rays to come in, you can, the lens will ensure that they converge and will get us to a better, sharper images than simply having a small pinhole for us. So yeah, now you see here, the whole idea from this one is just to make sure that the light, like when allowing multiple light rays to enter, that they converge and avoid the blurriness, like here, the blurriness that we had if you had a larger aperture. Now in a camera, so what we have is we have the light rays that are incoming. We have our lens. So anyone tells me again, what is the purpose of the lens? What do you think? You can type on the chat as well.
Hello.
Yeah.
Okay. Like from the previous slide, the purpose of the lens is to reduce the amount of easy rays that are coming into the camera, the light rays.
Sorry, can you repeat again, Grace, to reduce the amount of...
Okay, can you hear me?
Yes.
Yes. So from the previous slide, the purpose of the lens is to reduce the amount of light rays coming into the camera.
It will, okay, so I just to clarify, thanks Grace a lot for answering. So here, it's while it is not necessarily decreasing the amount of light rays, but it is making sure that they converge. Because if you have so many light rays and they're not converging, you end up with having blurry edges here. While if they are converging, you can have a sharper edge, while it is while still ensuring that it is not dark. So here, this is sharp and dark. This is light but blurry. So with the lens, you avoid this issue. It's an in-between. But thank you, Grace. So again, this is more to converge light rays and get it to have a sharper image. Now an aperture, this aperture is what controls how many light rays are going to go in. So you can have a small aperture, you can have a large aperture. So there is aperture size, is something in the camera that you can control. It's like one of the specs or like properties of a camera. And then we have something called shutter. So shutter, this is like, imagine that you are like you're watching a world in motion, right? Like some objects can be moving and so on. So a shutter is, it opens and then you allow light to enter and then it closes. So if you have something that is moving and you keep your shutter open for a long time, you end up having, let's say I have this ray moving. You will have a very blurry ray because you kept your shutter open until it moved from this point till this point. So a shutter can, if you want it to be sharp and for a very, like you open it and close it on a very small intervals, so you can control the amount of time you keep the shutter open and then close it, and that will control how much your image is going to be sharp, and accounting for motion blur. Because so something called motion blur is when you have an object moving and you start seeing blurriness around that motion of the object. So that's related to the time this shutter is kept open. Now, once the light rays, so you have the light rays going through the lens to get it to converge, and then the aperture, which controls like the opening size, and then the shutter, which controls the time, how much it will be open to allow the light to enter, and then we have our image sensor. So on the image sensor, what is the main idea of this image sensor is to take the light, which has at the end photons, and try to convert it into electrical signal. So at the end, you will have pixels. After the conversions, you will into discrete values, you will end up having these pixel values that we see on our machines. Okay. Of course, this is after again like converting everything to a digital image. So anyone has any issue with just again like the basic explanation of what is the camera, like the different main components there? Yeah, exactly. Thank you, Rachel. Sorry that I just saw it. So yeah, anyone else has any questions? No. Okay. I just want to make sure is my sound like you can hear me properly, or it's too noisy outside? Let me know.
I can hear you properly, but I don't know about the rest.
Thank you, Rachel. Okay.
On my case, I didn't get the main difference of the
Oh,
shutter.
sorry, Loyan, I can't hear you. Like you have to put your like your voice a bit high.
Okay, I was asking about what the shutter and the aperture does. For me, let's see if they do the same thing.
Yeah, that's a good question. Yes. Okay. So what is the difference between the aperture? Oops. Oh, sorry. What is the difference between the aperture and the shutter? So let me clarify here. So aperture, it doesn't change. Like it's just like think of it as a small opening, and you can have you can control the radius of the aperture, and that radius will control how many lights will enter, but it doesn't change. So it's part of the properties of the camera. You can change it by adjusting. So some advanced cameras can help you adjust the aperture size, but I mean while you're taking the photo, the aperture doesn't change. Okay, and it just helps. Like the whole idea from the aperture is that it controls the size, like the radius of this opening to control how many lights you want to enter, because controlling that amount of light can has an effect on the sharpness of the image and the whether it is dark or bright. Okay, so now this is the aperture. Any issue with the aperture, Loyan, or that's good? Okay, I mean, let me explain the shutter, and if you still have an issue, we can discuss. So the shutter, on the other hand, what it does is that it opens, collects light rays on the image sensor, and then it closes. So this is when you click that you're gonna take an image, the shutter opens for a certain amount of time. The amount of time itself is again one of the properties you can control in the camera, and then it closes. So with each time it opens and it closes, it again does control the time. So it's looking, the shutter will look into the amount of time. So how long it is open will control how what are the events, or like what are you actually capturing. Now, if you keep it too much, like for too long open, that can end up into having some higher blurriness when you have a moving object, because now it's not just you're capturing this object at once. Like if it opens and closes instantaneously, like in a very small fractions of second, then it will be quite sharp. But then if you increase it a bit and capture, like keep it open for more time, it becomes blurred. Like you get to see some blurriness around the edge of the object that is moving. Okay, does it? I'm not sure if this helps. Like again, I'm trying to explain it in a very layman terms. Yeah. Okay. Thank you, Leon. And so I will now proceed to the like the next part, which is more on the basic operations. So we'll talk about a couple of basic image operations, and then we'll talk about the image transformations in the next tutorial. So if we're talking about the basic operations, we have here like the basic one, of course, is convolution. So with convolution, like if you have worked with convolutional neural networks or any of these, most of the deep learning methods for working on images, you need to understand all of them are working based on this operation. So that's why it's important that we understand that operation. So how it works, you have your input image, So now this is a digital image. Like you have everything is discrete. Like you have these values now. Where we don't have now photons from the light. We don't have even the like it's not just the signal. Now we have actually the actual discrete values. And then we have our kernel. So our kernel is like the whole idea is that kernel gets to filter, get to be used to filter this image and have an output filtered image. So this kernel here, which you see, it's a 3x3 kernel. That is just simply doing, what do you think this this is doing? Like you see, each element here is 1/9. And we have 3x3 kernel. So we have 3 elements. So what do you think would be the expected output? Like what does this kernel do? Regardless of how it will be applied, but what do you think would this kernel do? So I have 3x3. I have 9 elements, and I'm just doing 1/9 in each one of them. So this will be doing what? Any suggestions?
What's the question? I didn't understand the question.
Sorry, can you increase your voice, Miriam?
I didn't understand the question.
Okay, let me increase the question. So you know what? I can tell you first how it will be applied on an image, and then I'll ask you at the end the same question. So if we're doing just simple convolution, regardless of what the kernel elements are, we're gonna take the kernel elements. Let's say this is our 3x3 kernel. I'm going to center it over each pixel. Now I started here with inner pixels, so I will start with the 2. This more is a boundary, like this here. So all of this column, all of these are boundary pixels. I will, for now, not talk about them, but I will talk about them in a bit. But if we're talking about these pixels here, if you are doing a convolution, the first thing you will do, you will center. Let me just do another color so it's a bit less confusing. So you will center the kernel on this pixel, and then start taking each element with the corresponding elements in the kernel and multiply. Plus this multiplied by this, plus 10 multiplied by 1/9, plus 4 multiplied by 1/9, and so on. So you end up having, you're taking 1 plus 5 plus 10 plus 4, all of these multiplied by 1/9, because all of these elements are the same here in this specific kernel. They're the same, which is 1/9. It doesn't have to be, but this is how you will do it in the first pixel, and then you end up with some number. So let's say it's 5. And I'm here showing that at the end, both kernels are the same. So if you take each element as 1/9, it's exactly the same as taking a kernel of all ones and then multiplied by 1/9. Now, if I want to move, if I want to do the convolution to get the next element, I'm going to move to, so I finished this one and I have this output. I'm going again to move to the next. So this is how convolution works. You're doing a sliding window. So you're going to move your 3x3 kernel, and now you're going to be centered around what I'm doing here. And then it becomes 5 multiplied by 1/9 plus 10 multiplied by 1/9 plus 13 multiplied by 1/9, and so on, until 11 multiplied by 1/9. So you're doing a dot product between your kernel and the region of interest, this small part of your image, and you keep doing that until and do a sliding window until you finish the convolution operation. So the next step will be to center it around this pixel and compute the corresponding output here. Now, if and again, I'm ignoring, so the boundaries, for now, I told you I will ignore, but we'll see that you can also process the pixels at the boundaries. So I computed this, I computed this. Now I need to continue with the sliding window. So I'll need to go to the next pixel in the next row. So now you're going to center it around this pixel here. And you will keep doing this until you finish all of your pixels in the inner, in this, all of these as well. And I'm showing here one pixel, which is at the borders. and we'll see how to handle the borders in a minute. But before we go there, I just want to confirm from my explanation of how to do the convolution. What do you think this kernel is doing? So this kernel gets to, you just do a dot product with this 3x3 patch in your image and compute an output. So what is it actually doing in this 3x3 patch?
Could you say that it's
Okay. Hello.
Yeah. Hello, Rachel and Daniel. Yeah.
Okay. To me, it seems like it's scaling down the image.
By scaling down, you mean reducing its size, or scaling down in what way?
It's I would say kind of the pixels in the image.
Sorry?
I mean, it's scaling down the pixels in the image. Like it's making it's not, things are not sharp. Things in the image will not be sharp anymore. They'll be a little more blurry.
It will become less sharp. It will become blurry because, thank you, that is true. Why? Because you're doing averaging. So exactly. So if you take this 3x3 kernel and multiply by this 3x3 patch, what you're doing is actually taking all the elements, adding it up, and then dividing by 9. This is just simple averaging or smoothing. So this smoothing effect will lead to a blurry, like a blurry image, and the size of the kernel can control how much your blurriness will result. And you can do it even as a Gaussian kernel. Like here, this is just simple averaging filter. You can do a Gaussian filter. But at the end, it will be less sharp edges. That is true. Thank you, Rachel. Yeah, let me know if anyone has any issue with what that filter was doing. Okay, so the last step in the convolution, I just want to show you how we are going to handle the border pixels. So we need to also know what pixels at the borders will do. So if I have like, remember, this is my borders that I ignored. So there are two mechanisms to do it. Either you're not going to do padding, so these are going to be ignored, or if you're going to do padding, then you can do padding with zeros or the same values. So if you're going to do padding with zeros, all of these are just going, like, it's like having a new row and a new column of zeros. Then when you need to compute the value for this, oh, I think, sorry, let me, I think I need to charge. Yeah. Sorry, one moment. I'll have to actually go inside. Yeah. Okay. So now we're back. Yeah, just making sure everyone is hearing my voice. Okay. So yeah, here. Let me just take this away. So if we're talking about like the border pixels again, so for the border pixels, we will just add zeros. Let me put that back. And if you can just pad with the same, so if you're padding with the same, you will just have to replicate what is on the border. So this becomes 1, 4, 3, 4, 3. This is another strategy of padding. And then when you're going to do the convolution, in order to compute the output from this pixel, you just center your kernel. So your kernel, which is just 1/9 all over the elements. So you will have 0 plus 0 plus 0 plus 0 plus 1 plus 5 plus 4 plus 2. And then this is going to be multiplied by 1/9. So this will give you the output of this element here. So that's how you will perform the convolution normally, but then you would get to know that actually most of the ways it is implemented, it's actually convolution is not exactly implemented like that. It's implemented rather as a matrix multiplication. But I just want to show you here. So this is again from the online course. Sorry, from the online course that I talked about. Oh, I think I'm not sure why this should be a video.
But
yeah,
because I mean, like last time I did this was at the university during my master, but I did like on signal processing. But is there also like folding, like the kernel when you before applying the metrics, you have to fold the kernel? But I'm not sure.
I'm not sure about the term.
Okay.
I gotta admit, I don't come from a signal processing background. So,
okay.
But it is true, like convolution exists in signal processing generally. It's not only a 2D signal, even in a 1D signal, you can do convolution. But I'm not sure of the term. I think I have heard that term before, but I forgot now.
Okay, just like.
But it is like, again, it can be for 1D, it can be for 2D. The whole idea is that, and I just wanted to show you here on this video, but you will see like this is, for example, one kernel that is learned within a convolutional neural network. So this is the kernel weights is what is actually being learned in the convolutional network. And these weights here just get to convolve the image in a sliding window, and then you keep doing that, doing this sliding window until you compute the final output exactly as we saw. But then we have multiple filter banks. So we have here like these correspond to the different channels. So sorry, let me check. Yeah, this corresponds to the different input channels. So like I have this is like red, green, blue. So I have 3 input channels. So this is the learnable convolutional weights for the 3 input channels. And then you have different filter banks. These are the output channels. So these, like I have 2 weights. So that's why I have 2 channels at the output. So this is how you like again in a very small like in a concise way to describe a convolution operation and how it works as a basic step in convolutional neural networks. Oh yeah, here now it works. I don't know why it wasn't. It's quite weird. Like the video wasn't working before. Yeah. Yeah, no, something is wrong with it. Anyways, so one last thing before we go into doing the convolution as a matrix multiplication, I wanted to show you if you're doing a convolution with a stride. So with a convolution with a stride, let me just clarify here. So if you are trying to do the same convolution, but now we have a stride of 2. So what you saw before was stride 1. So when you're doing the sliding window, you're always moving 1 pixel. When you're having a stride 2, so I start here with this border pixel. I center my kernel and I do dot product. I end up having this one. Now, when I go to the next, when I do sliding window and go to the next pixel, I'm going to jump 2 pixels. That's why what it means to have stride equal 2. So now I'm going to be centered around the 10, and I'm going to again do the convolution where I'm multiplying the elements by the different elements inside this 3 by 3 patch, and I compute my corresponding output. And I'm going to keep doing that. So I will have to go also to centered around the 2, compute the corresponding, and now I go down. And when I'm going down again, I'm going to skip 2 pixels. So like it's because it's stride 2, I'm going to jump with 2, and be centered around the 3. And then take the pixel here and so on. So you'll keep doing this convolution with stride. Just for I know a couple of you already have been working with like deep learning and are aware of like other operations. I'm just wondering, what do you think would be equivalent to doing a strided convolution if you have a stride tool, or like what is the impact? Like what do you see happened here from this full image to this? So if you do a stride tool, what do you expect will happen in the output?
Like you are reducing also the size of the original image.
Exactly, yes, thank you. So the strided convolution, you can see that it has some, so not only is doing convolution, but it's doing also what the pooling will do. So you can do pooling with kernel size 2, and it will do the same, where at the end, like this input height by width became height over 2, width over 2. So you reduced the resolution. Now, what I will show is here is the convolution as a matrix multiplication, and we will do actually the practical on that. And then we'll continue with the image gradients. I just want to make sure I'm not passing over the time. Okay, so we only have 10 minutes to cover the matrix multiplication part, and even the part for the image gradients. So you see here, we have our kernel, which is just a 2x2 kernel. So in how we will do the convolution operation, and this is our input image, where again, we're trying to like center our, anchor it around this 2x2 patch, do dot product. So it becomes 0x1, 1x2, plus 2x4, plus 3x5. And this will be the output of the first pixel here. And then you're going to go sliding window. So this is because here the stride is equal to, the reason I slide with only 1 pixel, the stride is equal to 1, right? And then I'm going to slide to the next and to the next until you end up getting this 2x2 output here. So this is now representing the exact same, but as a matrix multiplication. So the first thing you're going to do, you're going to take your input 3x3, the 3x3 input image, and you're going to flatten it. So this flattened version, which is just 1, 2, 3, 4 until 9, is will be just a 9x1 vector after the flattening, and then you're going to represent the convolution as a matrix multiplication. So for this matrix multiplication, you're going to take the 2x2 kernel here, and you're going to start filling it into this sparse matrix. So this sparse matrix is mostly zeros. And I'll show you how it works. So we see here we have 4, it should be 4x9, and we have here a 9x1. So you will end up with a 4x1 output, which when you reshape becomes the 2x2 we have here. So this 4x9, how it is done, if you remember, when I take this 2x2 patch and this kernel, I was trying to do this 0x1, 1x2, 2x4, plus 3x5. So this is what I'm trying to do, right? This can be just doing, with matrix multiplication, you're taking this row. Oh, sorry. You're taking this row here and then multiplying with the with our 9x1 vector. So this is how like you represent a convolution with a matrix multiplication. You can see by adding these zeros, so that's why it's a sparse matrix. By adding these zeros, you controlled how the kernel elements are going to be multiplied. So 0 is going to be multiplied by 1, 1 is going to be multiplied by 2, 2 is going to be multiplied by 4, and 3 is going to be multiplied by 5. So this will represent the first element 25, and then you can see that as you go, like as you slide your window, so this 2x2 patch will just correspond to the second row here, multiplied by the same 9x1 vector of our image. Again, these zeros just control how we are going to perform the sliding window part and get the final output. And then we're gonna do the same for the next row and the next row and so on. So you have 4 outputs. So that's why we have a 4×9 sparse matrix, a 9×1 vector of the input image, and a 4×1 output at the end when you multiply this matrix by this vector. So anyone has any issue with how convolution became matrix multiplication and how we started adding these zeros? Sorry about, I switched from Keynote to PowerPoint, so that's why the things are not adjusted properly. Yeah, anyone? Oh, okay, I see someone here on the chat. Oh, sorry, Memdiar. I think that was from another, a previous one. Okay. So if no one has any issue, I'll just proceed. So the next thing we'll try to look into, so explaining here how this convolution as matrix multiplication, you can, if you have a larger kernel, so instead of this 2×2 kernel, you have a 3×3 kernel. So this will end up having more non-zeros. So your matrix will change in that way. If you have a larger input height, so you will have more rows. So we'll have another 2 rows, for example, that needs to be multiplied with this vector. If you have larger input width, you will have to insert more zeros here. So again, we use these zeros to control how to convolve our image. So you will need to insert more zeros in this sense. Yeah, so I hope this makes it clear. So what we're going to do now, it's a very simple mini practical. I'll give you the like a collab, and I want you to just try to implement the strided convolution. So here is what you have. You have this input, and I provide you with that input, and then you have this 2×2 kernel. And I want you to construct it as a matrix multiplication. So you have your flattened input here. So this is a 4×4. So you end up having 16×1 flattened vector. And then I want you to compute this sparse matrix. No need to make it generic, like I don't want the code generic, just do the sparse matrix that will do this convolution. Taking into account, we're doing a strided convolution with stride 2. So let me, I mean, it's more like an in-class exercise, but I will only leave like 15 minutes. And yeah, let me post here. I think I should be able to share. See if I mean, can you try this and let me know if it works or you have any issue with it? So everyone received the collab. I just sent it on Slack. I can also send it on the chat here. Yeah. So yeah, let me know if you have any like do you have any questions regarding like what is the task? So you will find here. Let me okay. I think I'm now sharing from the other let me just put it here first. One moment. So here you will find this is the input image, this is the kernel, this is and this is what you like. You have your kernel here, and you have your input image. And what I want you to do, just try to implement it as a matrix multiplication and put it in output. And again, you can hard code it. I just want to make sure that you know how to do this stride 2 convolution as matrix multiplication and do the sparse weight matrix for it. To compute an average pooling. So Grace, for that one, we're not necessarily doing average pooling. So average pooling, you will you don't have a kernel weight that you're multiplying. So for this one, we have certain kernel weights. So we have this 0, 1, 2, 3 is your kernel, and you need to it will do something. It will amount to be something similar to pooling, except it's not the same. Because we have kernel weights that you need to do a dot product with each 2x2 patch in the image while doing the stride. No worries, no worries. I can even to make it a bit clearer on what we are expecting. So here, we're going to expect that we have this 0, 1, 2. So we'll have 0 by 1 plus 1 by 2 plus 2 by 5 plus 3 by 6. Whatever that output will be the first element here. So this will be the first element here. And then you're going to do stride 2. So we're going to jump 2 pixels. So initially I was at that pixel. I'm going to jump 2 pixels. So I'm going to be here. And then I'm going to do the same 2 by 2. So I have 0 by 3 plus 1 by 4 plus 7 by 2 plus 8 by 3. And whatever is here, this is going to be the next output and so on. But now we need to make it into a matrix multiplication. So first you can compute that output and then you can put it in a matrix multiplication. Yeah, so I mean, I'll leave you till, I have it here, it's 12. So I'll leave you till 12:15. And any questions you can ask me, and then we can continue the rest of the tutorial. I can also share with you something, like I can share with you what is the expected output. Or if someone actually computed it. Aha, exactly. So 30, 42, 78, 90. Thank you, Grace. So here, this is 30. Can you share with us, Grace, the exact sparse matrix you use? So this is like now that you computed the convolution, what was the sparse matrix you used? And 90 here. So this is the output, and that's correct. Anyone wants to share the sparse matrix? So we're gonna have, let's see. We are gonna have a 4 by 1 output. We have a flattened matrix that is 16 by 1. So what do you think the sparse matrix will be, the size of the sparse matrix? And what will it be, like what will be the elements inside? Any suggestions? I mean, you can tell me if you feel like it's where you're not sure what exactly to do? Okay, so Grace, you're not sure about the sparse matrix, okay? I want to check with others. So so for others, do you know how we got this first? Like what Grace gave us? Do you know how we got this first? Or anyone has any issue with this output, this 2 by 2 output?
I have an issue because I dropped off for a while due to some internet connection, so I'm not up to speed on this.
Yeah, of course. Let me explain it again, Rachel, for the convolution. So for this strike 2 convolution, you have here a 2 by 2 kernel. So how the convolution will work is that you will take, so we'll first center it on this pixel, take each element, do a dot product with the kernel here. So we'll have this here. We'll have 0, so 0 by 1, 1 by 2, 2 by 5, plus 3 by 6. So this is here. This will end up being 30. And then I'm going to do a sliding window, but then I have strike 2, so I have to skip a jump with 2 pixels. So I'm going now to the next pixel will be here, and then it will be centered here. And this is the 2 by 2 patch I'll be working with. So this 2 by 2 patch, I'll multiply it with my 2 by 2 kernel, like do dot product. So I have this second here. So 0 by 3 plus 1 by 4 plus 7 by 2 plus 8 by 3. And this will end up be giving me the 42. Does it make sense now, Rachel? And then the next one, I'll go to the like sliding window. So now I'll go to the next, I need to go to the next row. So I'm going to also jump with 2. So I'll start here at this point. So we go this way. We go this way and we go downward. And the jump, by how many pixels I'm going to jump, the stride is the one that determines it.
Okay, thank you very much.
No worries at all. Anyone has any issue with how we got that output here? So is it clear now? Okay, so if this is the case, no one has any issue. We're going now to go through how to do the sparse metrics here. So the sparse metrics, just want to make sure I have the, so here. So we have our flattened input. So this is a 4 by 4 input that we flattened. So it becomes 16 by 1 vector.
I think there is a question in the chat about the jump.
Okay, thanks, Miriam, for pointing that out. Yes, Loyan, not clear on my side about the stride jump. Okay, thanks for the question. So Loyan, we're having stride 2, which means that if I am at this location here and at this pixel 0, 0, if stride 2, I'm going to jump 2 pixels. So instead of 0, 0, it becomes 0, 2. I will start at 0, 2. And now I'm going to jump another 2 pixels. I already, like this is the end here. So I'm going to jump to 2, 0, and then 2, 2. This is here, these numbers are identifying the indices, I mean, in the image, okay? Does it make sense? Normally, the kernels are actually odd-sized kernels, but this is again for simplicity. So we're doing like a 2 by 2 kernel for simplicity. So Loyan, are you okay now?
Yes, I just wanted to ask about what about the elements that we skipped?
So here, you mean like, for example, we if we are having stride 1, I will instead, sorry, I don't know why it's not writing. I will have something in between like that, right? Because stride 1, I will have to do the sliding window at each pixel. I'm not jumping with the, I don't have a stride 2. So because we have stride 2, we are just going to jump, so there is nothing in between anymore. Like this just controls your sliding window. If it is stride 1, then you will have larger input. So it will not only be 2 by 2, it will be larger. And you will be sliding, when you're doing the sliding window, you will be you will be going through pixel. Does it make sense? So we'll have 1, 2, and 3, and then 9, 10, and 11. And now I'm not doing any padding as well. Like we're trying to make things quite as simple as possible. So no padding, and it's just like an even size 2 by 2 kernel and so on. Okay. Clear now? Okay, thank you, Loyan. Good. So if everyone is good with this, what I'm trying to get you, like try to draft it on a paper first. How can we get this convolution that we just did, like this? You see this row, and the other rows that will get us the 78 and the 90, you can write it yourself. Use it and construct it as a matrix multiplication. So in this 16 by 1 vector, I will have 1, 2, 3, 4, 5, 6 until 16. So this is a 16 by 1 vector. Try to get here a sparse matrix. You tell me first, what is the size of the sparse matrix? What are you expecting? Like in terms of like how many rows and how many columns?
Would it be 4 by 16?
Exactly, thank you. So it's going to be 4 by 16. So thanks, Daniel. So you can now work whether on code or like on a piece of paper, it's up to you, and construct this 4 by 16 matrix, sparse matrix. And use the zeros to control which ones. So let's say here I have, so my kernel, you will have in this sparse matrix the kernel elements. So you'll have the 0, 1, 2, 3. But here the 0 is multiplied by 1. So I can put here 0. And then what do you think else I should do? I don't want to like give it away. So I'll give you a little bit more, like a little bit, 5 minutes more, and then we can discuss the sparse matrix together.
But I have a question because when you create the sparse matrix, the 0, you can control as you want how to put them, or like there is a rule. Okay. That's
so you control it based on here. So these are the operations that we want. This is how the convolution, this is how we did the convolution. This is the output that we want. Now we're going to control the sparse matrix accordingly.
Okay. Yeah,
so
I see.
You see here, we talked about how larger kernel means more non-zeros, larger height, more rows, larger width, input width, more zeros in between, more sparsity in between. So yeah.
Yeah.
Even you can tell me, like if someone can give me what is the first row in this 4 by 16 sparse matrix, and then I'll leave the rest to you for later.
Is the first row 0, 1, 0, 0, 2, 3, and the rest are zeros?
Exactly. Thank you. So yes, thank you, Daniel. So it will be 0, 1. So these are here kernel elements. So this 0 is actually part of this kernel element and this kernel element multiplied by the 1 and the 2. And then we put here zeros because we need to make sure that it gets multiplied by the 5 and 6, right? So we need to skip here based on the height. So this is based on based on the width of the input. And then we put the 2, 3, and then the remaining zeros. So this will give us the first 30. So here, this will give us the first 30. And you can do the rest later as long as you understood that first part. So anyone now things are clear on how we do convolution as matrix multiplication? This is actually how it is implemented, and it's more optimized when you do it this way. Okay. So in the sake of time, I will try to skip ahead a little bit. So we have more time on the transformations one. I wanted to also introduce you something called image gradients and how to compute image gradients. This is part of the basic image filtering operations. So here, if you remember, we're talking about convolution generally. Now we're going to do convolution with a certain kernel that will get us to identify something called an edge. Okay, so an edge, it's a place where there is rapid intensity variation. So if I have here, this is here complete black. This part here, this is an edge, like this part here, this is an edge. So when you have complete rapid variation from this black to white, this identifies your edge. Again, sorry for like going from Keynote to PowerPoint, things changed and how here. Anyways, the like you can say that it is dependent on the first derivative. So your f is your function. So this is a 2D image. So it's a function of both x and y. And we're looking into intensity variation, right? Like anything that is like what is the rate of change is the first derivative. So except that we have a function of two variables. So we'll end up having a gradient vector where the gradient vector is just simply the partial derivative of our function f with respect to x and the partial derivative of f with respect to y. And we can compute. So this will be a full 2D image. And this will be another full 2D image. And this is what we call as image gradients. Okay, so this will capture the variations in our image in the x direction, in the y direction, which will give us the full and we can use it. So you know, generally you can use fx square plus fy square root. That will give you the magnitude, but you can also use it to get the direction, because so fy over fx can get you can use it to get the direction. It's a normal, like think of it as a vector. So you can use it to get the magnitude and the direction. And this will help to identify the change and the direction of like the magnitude of the change in the image and the direction of that change. Okay, so let's see how we can actually compute that. First, we can have here, like this is a step, a ramp. So a step, we went from black to white. And I'm looking, I took a slice of pixels. So I took only one row and I'm drawing it here. You see, I went from 0 to 255. In a ramp, if you take just one row here and try to like do an intensity profile, so like just visualize one row here, you go from 0 gradually into a 255. It's not a step, so it's called here a ramp. So because of this gradual change in the color. Same here, ridge, where you have change from 0 to 255 and then 0 again. Roof is from 0 to 255 and then 0 again, but gradual. So here it's gradual. Okay, these are different edge models. So you can see that this can construct an edge here, here, and here as well. Okay. So remember, I'm talking about the rate of, I'm talking about the edge represented as an intensity variation. So we'll look into rate of change. Rate of change means we're trying to compute the first derivative. Except that here I have 1D signal. Normally images are just 2D signal. I'm just here showing 1D signal first because it's easier that we understand. So if I take one intensity profile here and I'm showing the change from 0 to 255, and then going gradually to increase from 0 to 255, this is the intensity itself and how it is changing. So if you're trying to get the first derivative, here you see the rate of change. It's first, do you think this is increasing or decreasing at this point? So in this small square, what do you think? Is it increasing or decreasing? Any, let's see in the chat. I just saw now your question, Grace. The sparse matrix, I don't want to go back. Sorry, sorry for interruption. So we can take it offline if you still have that question. But I'm wondering, anyone wants to help? So in this small square here, this function, this is describing the intensity and how it is changing. So what do you think? Exactly. So if it is increasing, we will have a positive value for our derivative, right? And then until it peaks into a certain location, oops. Until here, this here will correspond to the peak. Okay. until so because here we're trying to change from a lower to a higher value, so the derivative will still be positive, and then oops. We're going to keep increasing until it's, you see here, it starts to plateau. So at this point, the rate of change, it increased until it reached that step. We're talking now about the rate of change. So this is here the intensity, and this is here the derivative. So when you see here, it starts to plateau. So the change is decreasing, right? So the change will start going back to 0 until you see here, it almost like there is no change. So it stabilizes. So here we start with all black, so very small change, and then it starts gradually to increase. So that's why the rate of change is increasing, and then it peaks at the at the location, sorry, of the edge, and then it starts to reduce again until it plateaus. Here is a full part of the image that is just all white. So there is no change. So that's why the change becomes back to 0. So you understand now why. So here, this is just like taking one row here. This is like your intensity profile. It goes from complete black up to a complete white. And then I'm plotting the first derivative of this intensity profile. That here the change is minimal. So it's minimal. And then it starts to peak. So here the peak. And then it becomes minimal again because it plateaus near the end. It's all white, like there is no change back. Does it make sense? Okay, good. Thank you. So if everything makes sense here, so this is what we will use. So if you know the peaks of your first derivative, you can identify the location of your edge, and that's what we will do to compute the edges. So here, remember, this was 1D signal. So in a 2D signal, we actually have the partial derivative of f with respect to x and the partial derivative of f with respect to y. And we'll start to see how we can implement that as a filtering operation. So if I'm trying to look for the places where there is edges, I can just look for the places where there is large variations, so large gradients. Gradients is the rate of change at the end, right? In both the x and the y. But then the problem is that if you have noise, so let's say here I have this salt pepper noise. So this salt pepper noise will also correspond to large gradients. So here, if I use, I didn't tell you exactly how yet, but if I used some image filtering mechanism to identify the edges, I will get the edges here of the, like you can see, I get the edges of the humans, but I also got the noise as well, like this salt and pepper noise. So that's why usually, if you want to detect edges, you need some form of blurring before. And you can do that with a simple convolution with a Gaussian. We have seen the averaging filter. This is a Gaussian filter. It's the same at the heart. Like it's not exactly, but it will at the end reduce, like it will blur. So the noise here will reduce. So when you compute edges, you get rid of the noise as much as possible. So how to compute the gradients we haven't discussed so far. Like we only understood what is a gradient, like does it mean to have a peak of change? And that this corresponds to the edge in the image, but we never talked about how to actually compute. So in fact, it is just another convolution with where you see that, if you remember, first derivative is generally approximated with forward difference, backward, and centered difference. So you can think of this as you have your current pixel. So you take the forward one minus yourself. This is the forward difference. Or you look back. So this is backward difference, or you jump forward minus the backward. So X here is the, like, whatever the current pixel you're at, and that's the center difference. So if I have it, you can just represent it as a filter. So here, this is average over a 3x3 filter. So I'm trying to, like, if I'm at this location here, I look back minus ahead. This will give us the change, the rate of change. You can do it even with smoothing, so that here, because these are closer to the center, so here they have higher weight. So this is called, this filter here is called Sobel filter. So Sobel filter can help you, if you take it, convolve with the image, you see there's some difference happening. So this is kind of, it's basically approximating the first derivative. And computing, you can use it to compute your image gradients. So here is a small trick though. We said that our image is a function of two variables, X and Y, right? Like it's a 2D signal or 2D image. 2D matrix. So we need to compute it with respect to the X. We need to compute it with respect to the Y. So this is here the gradient. So this is looking into the change in the X direction. This is looking into the change in the Y direction, right? So you tell me, if I'm looking into the change in the X direction, what would be am I detecting a horizontal edge or a vertical edge? So I'm looking into the change in this direction, in the X. So this is vertical or horizontal?
Horizontal.
Well, if you, okay, so if I have an edge here, like a horizontal edge here, you expect the change. So let's say this is black and this is, the change will be in the same direction or perpendicular?
Perpendicular.
Sorry?
I'm thinking, sorry.
No, it's okay. That's good. I'm happy that you're all participating. You can think out loud. It's okay. So here, when I go from black to white, and I have this edge here, you think the direction of the change is happening in the same direction of the edge? Or
no, it's perpendicular.
It's perpendicular, exactly. Because you see, this here goes from black to white, so it becomes perpendicular. So if I have this kernel, it will detect vertical edge. If I have this kernel, it will detect a horizontal edge, because you're taking the rate of change in the perpendicular direction.
Yeah.
So if I do this in an image, so this is here detecting a change in the Y direction, but it will get us the horizontal edges. So you see, these are, the horizontal edges are emphasized, horizontal edges, again, while the vertical ones, like these vertical edges, do not exist here. Now here, the reverse. I'm taking the change in the X direction. So vertical edges are emphasized. So you see these vertical edges, you put more emphasis. So after the convolution, so this is the output after the convolution. And you see there is more emphasis on these vertical edges. And here, nothing to emphasize on, because these are completely horizontal. Okay, so anyone has any issue? So this is image gradients. This is here when I say the partial derivative of fxy with respect to x, this is here. And it will result into a full 2D image. And this is again the partial derivative of fxy with respect to y. So this is what we call as image gradients. It's just images which capture the rate of change. It could be in the x, so in the x direction and in the y direction. Yeah, let me know if you have any questions. I see here the chat. Idris, yes, you were saying vertical. Sorry, Idris, I saw it late, but thank you. Okay, so if no questions, I'll go to the next one. I will not be able to cover all the full tutorial. So the tutorial actually shows you how to compute. So here, you will find how we can compute the edges. Like I have a checkerboard, and I show you how to compute the Sobel filtering output. So you are able to get the horizontal edges and the vertical edges, but I will not be able to cover it here. in the remaining 30 minutes, I think it's best that we go through this a little bit and perhaps continue more next time on this tutorial. Okay. So, so this tutorial here is introducing a bit of concepts on projective geometry. Next time we will start, so this is focusing more on 2D. So we'll talk about transformations, but all 2D, like 2D transformations only. And we'll specifically amount until understanding this, this type of transformation called the homography. And we'll see how to apply any transformation, even the simplest, like translation or rotation on images. So this is something called image warping. The next tutorial, we'll start looking into 3D transformations, and we'll start looking into camera models. So you will understand exactly how to project, because how to construct a projection matrix that projects 3D world points into 2D. Anything related to 3D vision, anything related to geometry and vision generally, you will have to understand these concepts here. Okay, so when we are talking about projective geometry, these are transformations that are trying to describe geometric distortion. So you see here, this is the original, right? Like it says, it should be a normal square, but because we are taking it with some camera angle, you see there's some perspective distortion happening. So all the transformations that are describing the distortion that happens under perspective imaging, this is what projective geometry is. And this is what we're going to discuss. At the end, we have a 2D matrix for our image that is f of x and y. So we're going to see how to translate first on a point level, and then we're going to see how to apply it on the full image, which is the image warping. So if I have one point here, let's say I have one point here on this checkerboard, x and y. And this x and y, I want to do a translation, like I want to move it with a certain in the x direction. So all I need to do, I want to take my input x, add to it a translation in the x, and I want to take my input y, add to it a translation in the y, and then get x bar, y bar, which is the output. So if I want to take this translation, but I want to describe it as matrix vector multiplication. You see, everything is getting represented as matrix vector multiplication. It's just easier. So I have my original point, x and y, and I want to describe the matrix multiplication as, the translation, sorry, as matrix multiplication. What do you think I can do? Or has anyone tried something like that before? Like doing translation, like I have an input point and I want to get the target point after translation. Yeah, let me look into the chat. Yeah, thank you, Grace. Anyone wants to help on this one? Like, how can yeah, how can I do translation as matrix multiplication? Anyone knows? No? Okay, let's do it together. So once you want to do translation as matrix multiplication, we start looking into something called homogeneous coordinate system. So in a homogeneous coordinate system, instead of having x, y only, we have also this one here. And this is, it actually not only for translation, like for now, I'll explain it to explain why we're, how to do a translation as matrix multiplication, but you'll see homogeneous coordinate has, like the homogeneous coordinate system has more meaning beyond that. But you will see that adding that one, you can easily describe translation as matrix multiplication by multiplying it here in this matrix. So if I have a simple identity, like, a simple identity matrix, but then with tx and ty in this column here, if you do matrix vector multiplication, you see that I take this row, so it becomes x multiplied by 1 plus 0 plus tx multiplied by 1. So this is what we are doing here. Same here as well. So this is describing translation as a form of matrix multiplication. And we did that by adding this one here, and we called this homogeneous coordinate. So we are now in the homogeneous coordinates. We're not in the original 2D. I mean, it's still 2D. Let me just be clear. It is still 2D. Everything here is still 2D. But we have this extra one, and I'll be describing it more next time. Yeah, so anyone has any issue with how we did this matrix? So here, this is the final matrix. So first, I'll check if anyone has any questions. Okay, no. Let me ask you then a question. How many degrees of freedom this matrix has? So by degrees of freedom, like, or this transformation has, generally has, degrees of freedom are the number of parameters that you can control that will amount to a change in this setting. So how many degrees of freedom? Yeah. Yes, Idris, one will indicate that there is only one parameter we're changing. But how many parameters you see here?
2.
Okay, so I see, Grace, you're saying 3. What are the 3? And Rachel as well. Why did you say 3 or 4? You don't have to say if you don't want to, but if you want, you can just open the mic and let me know.
Okay, so maybe I didn't get the understanding of the homogeneous coordinates well, but I think you can change x and then y and then t of x and then t of y also. But then one,
okay.
everything else is a constant.
Okay, now I understand why you said 4. Okay, so one thing, Rachel, thank you. We're talking about the transformation. So this is the original point. What you control when I say the degrees of freedom is the degrees of freedom of this transformation. So we're looking into the transformation matrix itself. So what are the, how many parameters we're controlling? The Tx and the Ty. Does it make sense? So this question is asking how many degrees of freedom for this transformation.
Okay.
You can take the same transformation, apply it on another point. So for this general translation as a transformation, there are 2 degrees of freedom. Okay. Now, thanks, Grace, also for letting me know for the number of rows. Here's the thing, for translation, you cannot change that row. So thank you actually for letting me know also about that. So this one, because it is translation, so nothing changes except these 2, because it becomes just addition. If you change this, it will amount to a different type of a transformation. It's not only translation at this point. So now that we agreed for the translation, it is 2 degrees of freedom, which is the Tx and the Ty. Sorry. Okay. Yeah, so it is a 2 degrees of freedom. Let's look into the rotation. Now we're gonna do as well a rotation as another transformation, 2D transformation. We're still working 2D. You can do 3D rotation, but we're gonna take it either next time or the one after. So let's say I have a point here, X and Y, and I want to do a rotation with some angle theta. So now after the rotation, I have X bar, Y bar. And I want to represent this rotation with some transformation matrix R theta. So you can see here, if I just look into the original point, X and Y, it has some angle with the x-axis, which is alpha. So you can say that this x here is just r cosine alpha. This is just simple trigonometry trig. So x is equal r cosine alpha, while and y is equal r sine alpha. Now, after the rotation, you end up having, now this is the x bar. So this is the x bar, y bar. So now I have, this is the new y, and this is the new here x. So this is going to be r cosine alpha plus theta. So this is this angle here. And y bar is going to be r sine alpha plus theta as well. Now, if you just look into the x bar, this r cosine alpha plus theta, you can, it can factors out into this. This is, again, trig rules. So we know from here that r cosine alpha is the x, right? So we can cross that out and just put x. And we can cross the r sine alpha and just put y. So x bar is just the original x cosine theta minus the original y sine theta. And this, we can just put it in a matrix here. So here we have x, y, and 1. And this is here the cosine theta minus sine theta. So remember the equation. So now if you take that row multiplied by xy1, we end up having this equation here and getting the x bar. Similarly, you can do it for the same. So y bar is going to be equal to x sine theta plus y cosine theta. So this is from this row here. So yeah, let me know if you have, so this is the 2D rotation matrix. Let me know if you have any question on how we constructed this matrix. Does it make sense? Let me check if anyone has any questions. Do you feel confused? Do you want me to go through it again? No, it's clear? Okay, so I'll move then from that. So what do you think? So you see with the, there is something called Euclidean transformation. So the Euclidean transformation is combining both a rotation matrix and the translation part. So we have the cosine theta, negative sine theta, cosine theta, and then we have tx, ty. When you do an Euclidean transformation, you will see that the Euclidean distances are preserved. So for example, if this is 2 centimeter, after you do the translation and rotation, this is maintained as 2 centimeter. And that's why it's called even Euclidean. So it maintains the Euclidean distances. It preserves the areas, like nothing changes in these ones. And the last one is that, sorry, I'm not sure if you already saw it or not, but what do you think? How many degrees of freedom this transformation will be? So for this transformation matrix, how many degrees of freedom you see? Yeah. Yeah,
Two?
thank you, Rachel. 3?
3, yes.
Sorry, who was talking?
Me, I'm sorry.
No worries, Miriam. Yeah, you were saying?
No, I was always thinking out loud. I was saying 3.
Oh, okay, yes. So it is 3, thank you. So 3, because what do you think, why the 3? What are the 3 parameters we're changing?
So I think the 3 parameters are theta, and then t of x, and then t of y.
Exactly, thank you. So this is the Euclidean transformation, and it has 3 degrees of freedom indeed because of the theta, tx, ty. Great, thank you. So also one thing to note that we have, if you're trying to rotate with respect to 0, 0, so this is what this angle will be like. It will, like, you remember how we derived even this matrix. So we're always rotating with respect to the origin. If you're trying to do a rotation that is anti-clockwise, then it's a positive, it's a positive angle. Now, if you're trying to move clockwise, then it's a negative. But that's when you are rotating with respect to the origin. In an image, things are flipped, right? Like the origin is up. It's like your axes are flipped, so things will change. You will see in the tutorial next time. I know we'll not be having the time to go through the practical today. But yes, so this is the positive and negative. There is another 2D transformation called similarity. So with similarity, not only we're doing rotation and we're doing the translation, but we actually are trying to scale. So we're changing the size, but then we're changing it uniformly across the X and the Y. So it's called isotropic scaling. Isotropic scaling, the term isotropic is indicating that is the same scaling factor in both X and Y. So here, this is a form of similarity transformation. You see this square, like it's still the same checkerboard. You didn't like it's basically just rotated and scaled, like became bigger, but it's the same scalar factor in both directions, X and Y. So how many degrees of freedom you think this will have? So degrees of freedom. And yeah, exactly. Thank you, Miriam and Rachel. So it's 4, and assuming that these are like the S, theta, Tx, and Ty. Exactly. So we have 4 degrees of freedom in a similarity transformation, and you will see it preserves the angles. So this is, for example, perpendicular. It will still be perpendicular. Nothing changes. It preserves parallelism. So things that are parallel in the origin after the transformation, they stay parallel. And we thought, yes, it's for DOF. Now, I can talk to you that you can do a scaling different in one direction from the other. So you can have here SX and this is SY. This is called stretchy. Something similar is called shear. So the shear is when you are modifying as well. Yeah, it's it's a bit different. So here you're just multiplying by a scalar factor. The shear is a bit different, but it also has like the scalar factor in the X and the Y will be different. So this is an example of like this stretch and shear. These are under transformations called they're non-isotropic, and they're under transformations called affine. So the affine transformation, yeah. Affine transformation is a 2x3 matrix here. This 2x3 matrix describes different forms of affine transformation. So anything with non-isotropic scaling, like once we have seen the similarity transformation. So what the major difference from the similarity to the affine is that the scalar from one direction to another changes. We have stretch, we have shear, all of these are under the affine, do not obey the similarity. And these are described by this 2x3 elements. So only 6 elements in this one. So of course the DOF just becomes at this point 6, right? Because these are just the parameters that we can control. It still preserves parallelism, but notice how it doesn't preserve angles anymore, right? Like here, this was a 90. Here, this becomes like like not necessarily 90 anymore. So, but the parallel lines stay parallel. Right, so we have 6 degrees of freedom. The final transformation you need to know in the projective geometry is the homography. So homography, it's a 3x3 transformation matrix. And what it does, it transforms from one 2D plane to another 2D plane. So look into here, like I have, this is the original 2D plane. Okay. So from this original 2D plane, you can take it to another 2D plane. And you can see that it does have, it's not just simple stretching or shearing, or it's not, it goes beyond the affine. So you see here, this row is not 0, 0, 1 anymore, like the affine. This is because it includes other perspective transformations. Like it can have this skewing effect. This can only be obtained by what we call homography. Now to do the homography, you actually need to have 4-point correspondences. So like I have here point A, B, C, D, and I need to make sure that I identify the ones corresponding to it after the transformation. Let's say it's A bar, B bar, D bar, C bar. So you're doing a mapping from one 2D plane to the other 2D plane. Okay, let me know if, does it make sense? What is the homography and how it differs from a simple affine? So a simple affine, this is 0, 0, 1. In a homography, it goes a bit beyond. Yeah, any questions about that? If not, I'll just then simply proceed. So what do you think? How many degrees of freedom this matrix has? And that's a trick question. I know it might look obvious, but this is a trick question, actually. So what do you think? How many degrees of freedom a homography have? I mean, the most obvious answer, what would you do? So for the affine, we had 6 degrees of freedom. For the homography, we have how many? Anyone wants to suggest? Loyan, yes, thank you, 9. That's the most intuitive answer, sure, because we have 9 unknowns. I mean, we have 3 by 3 matrix, we have 9 unknowns. However, it is not 9, it is actually 8. The reason it is 8, because we are taking into consideration the ratios with respect to H22. So you can always assume that this is up to this, whatever you're computing the homography, it's up to a scale. So assume H22 as 1. So everything else becomes H node node over H22, H node 1 over H22, and so on. So this is your matrix. So it becomes 8 unknowns, like 8 parameters or 8 degrees of freedom that you can change your transformation. And the reason, so if you have 8 degrees of freedom, how many, like you have 8 unknowns, you're trying to estimate how many equations you need and how many point correspondence do you need. So I have 8 unknowns because of the fact that, again, I have H node node over H22. I'm trying to estimate the ratio. So I'm estimating this homography up to a scale. So what do you think? How many point correspondence do I need to estimate this homography? At the end, I told you a homography is describing from one 2D plane to another 2D plane. So how many points? What do you think? Any suggestions? Yes, I see on the chat. One moment. So let me. 4, exactly, Mim Diara, thank you. So we have 4. Because if we have 4 points, so each point, like I can have here x, y, x1, y1, and x1 bar, y1 bar. Each pair will construct 2 equations. And then I have x2, y2, and then x2 bar, y2 bar. So this is another 2 equations. And you keep doing that for x3 and then x4. So you end up having 8 equations by having these 4-point correspondence mapped. Okay. So the minimum number of points we need is 4 to describe our homography, because we are estimating it up to a scale. So you see this homography, you can use it to remove perspective distortion. So I have here this image, I have this license plate, and I was able to, you see this perspective distortion here? I was able to warp this image and get the license plate number. You see removing the perspective distortion. So we agreed that we need 4-point correspondence between both. What do you think would be the point correspondence in this situation? So here I'm going to call this as the source points. I'm going to call this as the target points. And we only have remaining 5 minutes, so we continue the rest. So this will be the last question, and we can continue the rest next time. So what do you think would be the source points in this image? I'm trying to do perspective distortion, remove perspective distortion of this license plate. Any suggestions? So I have a license plate. I'm trying to remove perspective distortion. I'm trying to go from image A to image B. So I want to provide 4-point correspondence. So so I want to go from the source to 4-point correspondence in the target. What would be the source points in image A? And what would be the target points in image B? And if you feel like it's confusing, let me know. I mean, I can, we can discuss it in a different way. Any suggestions? So I have here, this is my image plane, and this is the new plane, the new 2D plane. So I have, I have this is the original 2D plane, and this is now the new 2D plane I'm trying to transform to. So this 2D plane is defined by the 4-point corners, right? Like the corners of the license plate. So if I define here, this is like x1, x2, x bar is the 4 corners. What do you think would be the target points? I'll leave you then to think about the target points. Not sure. Do you feel like is it confusing, like this part? I want to like get questions even if you have. What do you think? Anyone has any questions? Okay, so I mean, if you feel confused, we're gonna reiterate on this one again, but I can tell you that the target points will be like here, it will be like 0, 0, and 0 and width, and then height 0, and then, wait, sorry. So 0 width and height 0, and then height width. We can talk about what is height and what is width regardless. It's probably the reverse, right? Yeah, this should be the width and this should be the height. But anyways, this will define like the corners of the license plate will define your source points, and the corners of the image, the resultant image here will be the target points. And if you compute this homography, you can remove this perspective distortion. But I'll stop here. I know it could be like too much. And I'll just like present this summary here, and next time we can start from the same place for the homography and then continue with the 3D transformations and the camera models part. So again, just a summary that we have the translation, like we have 2 degrees of freedom. Euclidean has 3, where we add the rotation. Similarity has 4, where we add the isotropic scaling. Affine has 6 degrees of freedom, so it's like a 2x3 matrix. And then the homography has 8, because it's a 3x3 matrix, and we are always estimating it up to a scale. So the last element is 1, and then we are looking into the ratios, these ratios. And yeah, you see here, this is an example of like doing translation, Euclidean, similarity, affine, and the final homography. So projective is meant for the homography, what we call as homography, 2D homography. So I'll stop here, and let me know any questions you want to discuss. Okay, let me actually stop recording.